Now, because the columns of A are a basis for the column space, which is the same thing as the range, they are also in the range. That is, the basis vectors that form the column space. So the columns of A are also in the range of the matrix A. And therefore, they're also orthogonal to the residual vector. So that means that we can take the dot product of the columns of A, so A1 transpose, and the residual, and that should be equal to 0. Likewise, if I take the second column of A and dot that with the residual, it should be equal to 0 as well. Or if we want to do that entire dot product at one time, we could say that A transpose, the entire matrix, times the residual vector should be equal to the 0 vector. So now, since y star is also in the range, we can write y star equals A times x. In other words, we know that since y star is in the range, there must be an x and I'll call it x star here, such that y star equals A times x. That's exactly what it means for y to be in the range of x. So now we can take this expression for y, or this version of y star, and plug it into our formula up above. And then we have A transpose times AX star minus B equals the 0 vector. And this is starting to look a little more familiar to the formula that we were talking about earlier. So now let's just do one more thing. That is, we're going to distribute the A transpose through. And that means that we would end up with something that looks like A transpose A times X star minus A transpose B equals 0. And with a little bit of algebra here, we can manipulate this so that we have A transpose A times X star equals A transpose B. Just moving this term to the other side of the equation. And then lastly, what we want to do is we want to isolate this X star. This is our least squares solution, or will be our least squares solution. So we can do that a couple of ways to solve out for X. Ideally, if this is invertible, then we can multiply both sides by the inverse. And we haven't done a whole lot with that, but it looks a little like this if we can do that. So we would have that X star, which is our least squares solution, would be A transpose A inverse times A transpose B. And this becomes one of our generic formulas for finding that least squares solution. But again, what that predicated on was the fact that this is invertible. So if A transpose A, the result of that matrix, is invertible, then we can solve it this way. It turns out that A transpose A is not always invertible. Then what do? Well, we just revert back to our normal solving process. We would throw it into an augmented matrix and solve. So if the result of the product A transpose A is not invertible, then what do? Again, we throw all this into an augmented matrix. Remember, we know how to solve matrix equations here. So we can solve that matrix equation by taking A transpose A and putting it into an augmented matrix on the left side. And on the right side, we would take in A transpose B, the result of that product, and that would then be the vector on the right side of our augmented matrix. And then, of course, we would just row ref that and get a solution. To our least squares problem. So there you go. We've got two different ways essentially to solve it out. If you want to use this inverse method, we can do that. That's fine. There's an octave command, inv, for a matrix, say B, that will give you the inverse of that particular matrix. So we can definitely do that. We know how to transpose a matrix already in octave. So we can make the computation transpose of A times A and then ask it to find the inverse of that resulting matrix. If it doesn't exist, then we would find it out then. And if it does exist, then we could go ahead and make the computation using this formula. If it doesn't exist, again, the idea is that then you have to jump down and use a row ref process to solve that out. It might be a good idea that you actually practice both of those methods just in case you encounter something that doesn't have an inverse.